Today we're going to talk about energy changes of chemical reactions. So first of all, chemical reactions can be exothermic or endothermic. So exothermic, that means energy is released. So for instance, like a fire where you're releasing all this energy of the reaction. Or if energy is absorbed, the reaction is endothermic. So whenever you take in energy, it's endothermic. Before we go much further, I wanted to point out this figure just because I don't want it to confuse anybody. Figure 9.7 in your textbook is incorrect, whereas figure 9.9 is correct. The little caption of figure 9.7 said everything correctly, but then I think they just repeated this figure instead of putting in the figure they meant to draw. Figure 9.7 should have a reaction well that looks more like this, where your reactants are up here and your products are down here, and therefore have a negative energy. Whereas this one has a positive energy, and that's why figure 9.9 is correct. Okay, so let's look at this figure. What's going on here? Over here, you have a reaction, where these are your reactants, nitrogen and oxygen. And what happens in order for them to produce nitrogen monoxide is they must come together with a sufficient amount of energy in order to produce nitrogen monoxide. And so this is actually an endothermic reaction, because if you look right here, they have to have all of this energy. They have to climb up this huge hill before they could ever produce their end product. And so it's called endothermic reaction because it requires energy in order to produce the product. Another way of telling this is that it's got a positive energy required per mole for the reaction to take place. So every 1 mole of product that you want to produce, you need to have 182 kilojoules of energy. So figure 9.7 incorrect, but figure 9.9 is correct. So what we're going to be talking about today is how to tell whether or not a reaction is endothermic or exothermic, just simply by looking at bond energies. So the change in energy from reactants to products is due to either the formation or breaking of chemical bonds. Because if you think about it, with the last example over here, in order to form nitrogen monoxide, nitrogen had to break the bond between the two ends. It had to break the bond between the two O's, and then it had to reform the bond between each individual nitrogen and with every individual oxygen. And so for every reaction, you're breaking bonds and you're forming bonds. So the question is, are the reactants bonds, the formations, the breakage of the reactants, does it produce more energy or does it require more energy than that of the product? And so positive energy is the energy absorbed as bonds break. And so as you're breaking bonds, it's endothermic. And so it's positive energy. And so that's why your reactants, as you see down here at the bottom, always have a positive energy associated with them. Because as you break bonds, energy is going to be absorbed and it's going to be a positive energy. Whereas negative energy is the energy released as bonds form. So as bonds come together, they're going to release energy, and that's exothermic. It kind of seems counterintuitive, but if you think about it this way, as bonds form together, that's allowing substances to become into a more stable state. And so that more stable state is not nearly as high of an energy as the individual atoms are all by themselves. And so they can release that extra energy that they had, that they needed in order to exist individually. And so as they come together and form a bond, they're going to release energy. So this energy that it takes to break or form a bond is called bond energy. And they've actually classified it based on every individual bond that's possible. Here we have a list of selected bond energies. So this is the energy that's stored in each of these bonds. So if you think about it, a couple of them. Let's look at some of them. So with nitrogen and nitrogen, what do you notice? The triple bond contains a lot more energy than the single bond. And if you think about this, this kind of makes sense. If you were to, like, for instance, wrap something up in duct tape and just put one wrap around it, it takes a little bit of energy to break through and tear apart open that duct tape. But if you wrap it a whole bunch, then it's going to be a lot harder to open. As jokes, sometimes we would wrap presents for all the different kids in my family. We used to just wrap the present entirely in tape. And just seeing some of the frustration, probably isn't the greatest thing in the world, but more tape you put on, the harder it is to open, the more energy it takes. And that's kind of how it is with bond energy. Going from a single bond to a double bond to a triple bond, you're just going to increase the energy required. Also, you've got other trends that you can look at. So kind of hydrogen to hydrogen, 436. Hydrogen to carbon, 414. Hydrogen to nitrogen, 389. Hydrogen to oxygen, 464. And so you just kind of can look at this and kind of see the different bonds and how their energy relates. You compare the C to C triple bond with the C to C to single bond, and that's a huge amount of energy. And even comparing, for instance, nitrogen to nitrogen single bond with the hydrogen to hydrogen single bond with the carbon to carbon single bond, just kind of think about it and kind of think about all the different reasons why that could be. Think about atom size, think about electronegativity differences. There's a lot of reasons why reactions and bonds store the energy they do. All right, so how do we use this information, the energy stored in a bond, to figure out whether or not a reaction is endothermic or exothermic? So for instance, can you look at an equation and decide whether it's endothermic or exothermic? So when hydrogen reacts with oxygen to produce water, is the reaction exothermic or endothermic? So let's do this one. First off, you have to write out the reaction. So what we have is hydrogen plus oxygen yields water. Now, is this correct? No, for a couple of reasons. First of all, hydrogen, at room temperature, how does it exist? As a diatomic atom. Same thing for oxygen. Is it correct now? No, why not? It's not balanced. And so how do we balance it? Put a 2 in front of water and a 2 in front of hydrogen, because now there's 4 hydrogens on both sides and 2 oxygens on both sides. The next thing that you have to do is you have to figure out what bonds are contained in each one of these atoms and molecules. So in order to do that, you have to write out the Lewis structure. So we have 2 hydrogen molecules. Oxygen, how does that exist? Count up and make sure I did the Lewis structure correctly. There are 6 electrons on each oxygen, so you should have a total of 8 on both, but then you should have a total of 12 total available for the for the molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I drew that correctly, and hopefully by now you can draw the Lewis structure for water. Okay. So now what you do is you take all of your reactants and you figure out the bond energy for each one of them, and then you subtract the bond energy of each of our products. So here are our reactants on the left and our products on the right. So if we look, how much energy is stored in a hydrogen to hydrogen single bond? 436 kilojoules per mole. So it's 436 kilojoules per mole times how many moles of them do we have? So we have 1 hydrogen to hydrogen bond, 2 hydrogen bonds. So we multiply that by 2 moles. Plus, now we've got 1 oxygen to oxygen double bond. Come back over here to our table, 498 kilojoules per mole. Times 1 mole. Okay, because we only have 1 of them. Then, over here, all of these products are going to be negative. What types of bonds do we have here? Well, we have a hydrogen to oxygen bond. So we look on our table, hydrogen to oxygen bond is 464 kilojoules per mole. And how many moles of them do we have? So how many bonds do we have? 1 bond, 2 bonds, 3 bonds, 4 bonds. So we have 4 moles of them. And this is going to be negative because it's a product. So notice our moles cancel out. So our units should always just be in kilojoules. So what that equals is we have 436 times 2 gives us 872 kilojoules plus 498 kilojoules minus 464 times 4, 1856 kilojoules. And what that equals then, let's type that into our calculator, 872 plus 498 minus 1856 gives us 486 kilojoules of energy, and it's negative. Okay, so whenever we look at our bond energies, what that means is it's got a negative 486 kilojoules of energy associated with this reaction. So let's go back and let's look and see what that means. So if it's a negative energy, then the energy released as the bond forms is exothermic. So meaning that there is more energy released as the bond forms than was absorbed as the bonds broke. So our reaction overall is exothermic. All right, let's do another example. So you just kind of want to break it down just like this, where you write out the reaction, draw the Lewis structure so you can see what bonds are involved in the reaction, and then correlate bond energy with the number of bonds, positive energy for reactants, negative energy for products. All right, so when hydrogen reacts with nitrogen to produce ammonia, is the reaction endothermic or exothermic? So we need to balance it. So now there are 6 hydrogens on the left, 6 hydrogens on the right, 2 nitrogens on the left, 2 nitrogens on the right. So let's draw out our structures. There are 3 H2s. There's 1 N2. And then NH3. Okay, and there are 2 of them. Okay, so let's do the exact same thing as we did before. H2, 436 kilojoules per mole. Times how many moles of them? 1, 2, 3 bonds. Plus, because it's a reactant, we need to find N triple bond, which is 946 kilojoules per mole, times how many moles of them are there? There's only 1 bond. Even though it's a triple bond, there's only 1 of them. Minus, now we need to find N to H. N to H is 389 kilojoules per mole. And notice I'm subtracting here because it's a product. Times how many moles? 1, 2, 3, 4, 5, 6. So 6 moles. Now we're going to want to type this into our calculator. 436 times 3 gives us 13.8 kilojoules plus 946 kilojoules minus 389 times 6, 2,334. And then type that into our calculator. 1,308 plus 946 minus 2,334 gives us a total of minus 80 kilojoules. So once again, is this endothermic or exothermic? We go back and we look at the same idea. This is exothermic once again because it's negative. So exo. Alright. I challenge you just kind of for extra credit if you'd like, figure out whether this reaction is exothermic or endothermic. So it's a great deal more difficult, but I think it makes good practice. So here you have toluene burning in oxygen to produce water and carbon dioxide. So here's a picture of toluene, and so basically you have to count up every C to C double bond, every C to C bond, single bond, and every C to H single bond. And also at the bottom right here, you'll see that C to C double bond energy is 614 kilojoules per mole. So kind of interest, you'll need this in addition to that chart on the other page. So break it down and give it a try. If you want to email me for extra credit, you're definitely welcome to do so. So let's go look. I hope you now have seen how to use bond energies to figure out whether or not a reaction is endothermic or exothermic. Now we're going to look at some of the rules, some of the laws of thermodynamics. So the first law of thermodynamics is that energy is conserved in a chemical reaction, meaning you can't create it out of nowhere and you can't use it with, it has to all have come from somewhere. It's not created nor destroyed. You can't destroy it, you can't create it, you simply pass it along, pay it forward. Thermodynamics is the area of science that's concerned with energy's roles. And so that's really why we're looking at thermodynamics today, is trying to examine energy's relationship in a chemical reaction. So the first law of thermodynamics states that energy does not disappear nor disappear. It's not created, it's not destroyed. The second law is related to that, except for energy tends to disperse or become more disordered. And so this is kind of the idea that if you go into your room, let's say your dorm room, and it's nice and clean, but then you don't spend any time or energy in keeping it clean, what's going to happen to it? Dust is going to accumulate, stuff's going to get disordered, it's going to look a lot worse in a couple weeks. That's kind of what's going on with the second law of thermodynamics. It's saying that naturally things tend to become more disorganized. And so this is one of the main driving forces of chemical and physical changes. The idea of if the product is more disordered than the reactant, then the reactant is going to be pushed toward the product because the product is more disordered. And this name for this is called entropy, where entropy is the measure of the spread of energy. If you increase entropy, you increase disorder. So it describes whether or not a reaction is spontaneous too, meaning if things are going to naturally become more disordered, that means they've got entropy. They've got a large amount of entropy, and so the reaction is going to be spontaneous, just as your room will spontaneously get more and more disordered over time. I like this picture where it talks about the sun is truly a hothouse because basically it takes a huge amount of energy, and it's simply all the energy is coming from exothermic nuclear reactions. The sun is producing all of this energy, but only a tiny fraction of that energy drives photosynthesis. And basically that's its way of saying, let's take all of this energy that's contained within these nuclear reactions and just spread it out throughout the universe. Just spread it out. It's going to naturally disperse it. And so the sun is kind of one that naturally, it's spontaneously going to spread that energy out. It's not going to keep it all within its core. It's going to spread it out. And so chemical reactions are naturally driven by the spread of energy. And so think about all the reactions that the sun then goes on and facilitates. And so basically the sun spreading out into the energy, that energy is absorbed, so endothermically absorbed by the plant, and the plant spreads its energy out to people like us as we eat them, consume that energy, spread it even more. And so energy is continually just spreading throughout the universe. So kind of to recap, bond energies can be used to determine whether a reaction is endothermic or exothermic. Positive energy is endothermic, while negative energy is exothermic. Energy is conserved in a chemical reaction, and entropy is the tendency toward disorder.